Welcome to the Unit 13 guided practice for the remediation packet, starting with nuclear equations. It says predict the products of the nuclear equations. So in our first one, we see that we have plutonium. It produces a helium in an alpha decay. And when we're balancing these out, the one thing that we want to focus on is the mass number on top has to equal on both sides. So we started with 242. We already have 4 over there, so subtract 4, and we go to our 238. Then on the bottom, we see the atomic number also has to match, so we have 94. We already have 2 over there, so 94 minus 2 gives us 92. Now to find the symbol, or what the element actually is 92 protons, which is uranium. Going backwards, or the next one, we see we're going backwards. We have 32 on top on this side, and so we need 32 over here. Now we have 16 and minus 1, which 16 and minus 1 is a total of 15. So we need 15 over here. And the element that has 15 protons would be phosphorus. Moving on to our next one, we have Californium, and some element that produces 3 neutrons, because there's 3 right here. And we see that we have 3 and the mass number is 1, so 3 times 1 would be 3, plus our 259. And so what we would get is we get 262. Now on this side, we also need 262, but we have 252 there, so that means we need a 10. On the bottom, we see we have 0 and 103. And that means on our other side, we are going to need 103 as well. So that means that that would be 5, because 5 plus 98 is 103, and that is boron. With iron, we see we have iron, which is 55. On this side, we have 55. So that means that has to be a 0. Here we have 26, and then we have 25. So that means that is a negative 1. And we see that that is, put an E for a beta particle. And then oxygen. We see we have oxygen. We have 15 on this side. We have a 0, so this has to be 15. We have 8 on this side. That means we need 8 on this side. We already have 1, so that means it is going to be 7. 7 protons would be nitrogen. It says write a fusion reaction involving deuterium and carbon. So deuterium is hydrogen with a proton and 1 neutron, so a mass number of 2. And then we'll have carbon, so carbon 12, and carbon has 6 protons. And then it's a fusion reaction, so they're going to combine to make 14. 2 plus 12 is 14. 1 plus 6 is 7. And then nitrogen. Next, it says write a balanced nuclear equation for alpha decay, beta decay, and gamma decay. Some hints on this one. Alpha decay produces a helium. A beta decay produces a beta particle, which is 0, negative 1. And a gamma decay will produce a gamma particle, which has no mass. So any equation that we can use using these 3 would be a proper equation. D, it says what is conserved in a nuclear reaction? Energy is conserved. So we see that our mass is going to change, and when our mass changes, it turns into energy. And so energy and mass is always conserved through Einstein's equation of E equals mc squared. And so even in nuclear reactions, when we're producing a massive amount of energy, some of the mass is turned into that energy. Moving on to nuclear equations, talking about half-life, and it says a 10-gram sample of iodine 131 has a half-life of 8 days. And what half-life means is just the amount of time that it takes for half of the sample to decay. Now, it was determined that the original sample was 80 grams. When was the iodine 131 created? And so we started with 80, and now we're at 10. So a half-life would be, one half-life is when 80 gets divided by 2, and it turns to 40 grams. And then that 40 grams, that's one half-life. And then another half-life would be when that 40 grams is divided by 2, and it gets turned into 20 grams. So that would be two half-lives. And when that 20 grams is divided by 2 and becomes 10 grams, it was 3 half-lives. So we have 3 half-lives, and if each half-life took 8 days, 8 times 3 would give us 24 days. Determine the half-life of the sample based on the graph. So a half-life is when we have half of its original mass. So if we started with 200, half of 200 would be 100. And we see that that hit right there. So we go down. And if this is in time in seconds, that's 1, 2, 3 seconds would be the half-life. How can a geologist use uranium to determine the age of a geological formation? So if we know the amount of time it takes for a single half-life of uranium, what we can do is we can look at the amount of uranium in a sample, and then we can determine from its original composition how many half-lives it took to get there, and we can determine the age of a sample. True or false, during a radioactive decay, the same amount of material degrades every half-life. Justify your answer. So let's think about this. Yes, half of the sample is decaying, but on our first half-life, we went from 80 to 40. Second half-life, we went from 40 to 20. Third half-life, we went from 20 to 10. So is it true that the same amount of material it degrades every half-life?